or the rate of reaction. And for example, like coffee. If you have hot coffee, let's say we have hot coffee here, how long does it take to cool back down to room temperature? Is that something you can calculate easily? So let's say you have some coffee, it's at 80 degrees C. How many minutes will it take to reach 25 degrees C?
Depends where you put it.
Depends on where you put it. Like in this room, for example.
In this room, it probably be
There's the equation.
Yeah, what we want to do is this. We want to just kind of model it. Not model it, but we just want to do it by empirical observation. And so what we do is we just track the coffee. For example, does the coffee cool down linearly? That is, at a constant rate. If the coffee cools down linearly, then it's very simple to predict because, you know, we can describe this linear equation by this line y equals mx plus b. And if we have the equation of the line, then we can make some predictions, you know, how long it would take to cool down, right? But does coffee cool down linearly? What do you think? No, it doesn't. It cools down non-linearly. And so it actually doesn't cool down like this. Coffee cools down like this. And so the hotter the coffee is, the faster it cools down, but as it approaches room temperature, then it really slows down. And so what we see is a non-linear cooling curve like this. Non-linear. When we have a non-linear curve like this, you know, then the math is a little bit more difficult. For example, if I want to predict how long it takes to get to a certain temperature here, then I need the mathematics of this. And what did I say? If we have something where, you know, the cooling rate is continually changing, that is, the cooling rate's very rapid up here, but the cooling rate is slowing down as we go down here. When we have something with a changing rate like this versus a constant rate, then we need, what do we need? Algebra won't do it. We would need calculus. And so Newton came up and fitted this. We called it the Newton's law of cooling. Have you heard of Newton's law of cooling?
Yeah.
Yeah, so Newton's law of cooling, cooling happens exponentially like this as you approach ambient temperature. But does Newton's law of cooling, well, why? Why doesn't coffee cool linearly? Why doesn't it cool at a constant rate? Why does it cool like this? Does Newton's law of cooling describe why it cools nonlinear versus linear? No, Newton's law of cooling is just a mathematical equation that fits this. It's an empirical equation. This is an equation that fits the data. If we want to understand more, you know, should coffee cool like this or should it cool like this? And what's the difference? Then that would require some theory, a theoretical understanding of matter, right? Well, the first part of chapter 20, kinetics, is purely empirical. All we want is we want to understand the mathematical equation that describes the rates of reaction versus the rates of cooling. So we're going to be looking at the rates of reaction. The rate of cooling, rates of reaction is very similar. The only difference is rate of cooling, we're looking at how the temperature changes with time. Rate of reaction, we're looking at how the concentration changes with time. And so that's what we did here. And so for your crystal violet chloride, we were able to track the concentration versus time. Did the concentration change linearly or did it change non-linearly? It changed non-linearly. If it changes non-linearly, then we have two common options. And so here, rather than hot coffee, we're looking at the concentration of A versus time. And so it was not linear, it was non-linear. Then there are two common nonlinear. Curves that we should recognize. And so what are the two common ones? Well, we give them a name. For example, if it is linear, we call this zero order. decay or zero order kinetics. And what we're looking at here in this case is we're just looking at a single reactant, AA goes to product. Single reactant. And so an example of a single reactant reaction would be like KClO3. KClO3 decomposes into KCl solid plus 3/2 O2 gas. And so this would be an example of a decomposition or single reactant. This one is actually not a redox, but this one turns out to be an acid-base type reaction. Or no, wait a minute, this is a redox. Sorry, this is a redox because oxygen goes from -2 to 0. And so this is redox. Chlorine goes from positive to a negative oxidation state. And so here, so if we were to track the KClO3, we wouldn't track the concentration because the concentration doesn't change. We might track the amount or something like that. Or we could track the formation of O2. That would be something that would be easy to track. But if it's like this, then we say that this is zero order. The origin zero order comes from this. If we look at the slope here is delta concentration over delta T. And so the slope, which we call the rate of change, it's the change in A over the change in time. So how much did A change over this time interval? And so the slope is the rate of the reaction. Well, the rate of reaction is constant. And in fact, we like to use absolute value because we like to have positive rates. And so this would be the absolute value of the slope. And if we see how that depends on the concentration, the way we write that is by this. We have that equal to K, which K is called the rate constant, times the concentration of A raised to the 0th power. The concentration of A raised to the 0th power is just 1. And so this is just equal to K, rate constant. And so the rate constant is the rate in this particular case. And we call it zero order because it has no dependence on the concentration. That is, as the concentration changes, the rate stays the same. And so this is zero order in the concentration of A. However, this is not zero order in the concentration of A because as A changes, the rate does change as well. And so there are two common ones that we got to look at. One is first order in A. First order is easy to recognize. There are like 3 ways we can recognize as first order. One of the easiest is by something called the half-life. The half-life is if you take the initial concentration, you cut it in half. How long does that take to get to here? And so we cut the concentration in half. It took this long. Well, the time interval is T1/2 for the half-life. And so if we take this as our new initial concentration, cut the concentration in half, we're here. How long did it take? Well, if it's first order, it'll take the same time interval. So this will be T1/2. In fact, this would be 2 T1/2s. So we have 1 T1/2 for the first interval, and then a second T1/2 for the second interval. And then we'll do it again. We'll cut this in half. How long does it take? It takes actually the exact same time interval. So this would be at 3 T1/2s, or 3 of these T1/2s put together. And so what we see is this. This T1/2 is a constant. That is, it takes the exact same amount of time each time we cut the concentration in half. And so we can draw the curve here like this. We call this first order decay, first order kinetics, or first order curve here, and that would be an exponential decay. And so this is like the cooling coffee. When you look at the cooling coffee, as the temperature gets cut in half, the rate does come. Well, cooling coffee is a little bit more complicated, but because it approaches 25, not 0. So or whatever ambient temperature is. But essentially, it's the same thing. Okay, now we have a couple of things here. The rate here of change is the change in A over the time period over here. And the same thing here. we have different things. For example, here, the rate at this particular time, t, just say, what is the rate? Well, the rate is going to be equal to the slope of the tangent line at that particular time. So if we look at the tangent line here, we'll get this one as our rate. And so we'll have delta A over delta T. This pen is doing here. So this is delta A over delta T. All right, at this time, delta A over delta T, this is called the instantaneous rate at time T. You know, it's the rate at that time instant. So instantaneous rate at time T. Now, that rate is going to change in the next second. In the next second, you know, it's getting slower and slower as we progress. And so the instantaneous rate continually changes with time here. In fact, well, when we observe this, what happens with the instantaneous rate is the instantaneous rate initial, which would be the instantaneous rate or the initial rate at time 0, if we cut the concentration in half, what happens is that the instantaneous rate gets cut in half. In other words, what we see for this is each time we cut the concentration in half. So let's start here. We cut the concentration in half, which would bring us about here, and we look at the instantaneous rate here. The instantaneous rate here at half the concentration is half the rate. And so in other words, the rate behaves like this. The rate is going to be equal to the slope. Actually, since people don't like negative rates, they'll use the absolute value of the slope. And so here's our slope. This is the instantaneous rate, which is the slope of the tangent. And what we see is this behavior. That is, the rate is going to equal this k, which is a constant, called the rate constant, times the concentration of A to the first power. And so the origin of first order comes because of the first power here. And so in other words, if we cut the concentration in half, 1/2 to the first power is 1/2, so the rate gets cut in half. If we cut the concentration by 1/4, then the rate gets cut by 1/4. In other words, the rate is directly proportional to the concentration. And so the instantaneous rate here at this time interval, if this is half the concentration of the original here, would be half. Okay, that's a little bit more difficult to recognize. So it's a little easier to recognize the constant T1/2 versus looking at the slope of the tangent. Analyzing the slopes here is not so easy to do, but this is how they behave if we did that. Now, we have the instantaneous rate. We also have something called the average rate. And so if I pick these 2 points, this point here and this point here, we see that the rate here is double the rate here because the concentration is double that. But if we look at the average rate is going to be the average of those two slopes. And so the average rate is we just connect these 2 points. And so if I want the average rate between T1 here and T2 here, call this T2, then the average rate, we just connect a line connecting these 2 dots. And so the average rate would be the average of these 2 instantaneous rates, or just the slope of this line that intersects these 2 points. So this would be called the average rate here. And so delta A concentration over delta T is equal to the average rate over the time interval T1 to T2, T1 to T2. Okay, and again, they don't like negative signs for rates, so we'll take the absolute value. This is why it's so hard to calculate. I mean, if your coffee is cooling like this, you know, then the rate of cooling is continually changing, so it makes it very difficult to calculate. And the same thing here, you know, how long does it take for 95% reaction? Or after 30 minutes, how much is left? You know, those types of calculations are difficult. And so the way we do that is by this. We use a little bit of calculus here. Calculus is not required for this class, but if you use some calculus, then we can get these equations to fit this. And the equations we get, there are two forms for this one. One form is the ln of the concentration at time t is equal to minus kt plus the ln of the concentration at time 0. And so this equation has the form y equals mx plus b. And therefore, if we make a plot, if we plot the natural log of the concentration of A versus time, then natural log of A versus time, this is the time interval, delta t. And so t is equal to delta t. T final minus t initial. It's the time interval. It comes out linear, so this would be a straight line here. And so it would be non-linear here, but it would be linear here. So this is the third way. So there are three ways to determine if it's first order. One is looking at the half-life constant. Two is looking at the slope, the instantaneous slopes. You know, if I cut the concentration in half, did the slope get cut in half? Well, that's a pain. Three is making a plot of ln of A versus t. If a plot of ln of A versus t is linear, then we're good. This is first order. If it's first order, then we can calculate the concentration at any time, or we can calculate the time interval required for any concentration change. And so this is the mathematics of this. Where did this equation came from? This equation came from the calculus. And so you don't have to worry about it. And Newton, you know, Newton was worried about how fast things cooled. And so he had to develop some mathematics along with Leibniz to come up with the calculus. All right, now another form of this exact same equation. For calculations, this might not be the most convenient form here. For calculations, the most convenient form is to take the property of logs and do ln of A at time t over A at time 0, which is equal to minus kt. So this is the form that's most often used for your homework calculations if it's first order decay. So that's first order. All right, the other type of nonlinear curve that's commonly encountered is the second order decay or second order reaction. And for second order, it's going to look slower. And if we look at it based on half-life, so here we cut it in half. Let's say it takes this long. And so we call this T1 half, the time it takes for half. And then we look at the next half-life. And so we cut it in half. But in this case, it takes twice as long. And up here. And so this is the second half-life. So the first half-life, the second half-life. The second half-life is 2 times the first half-life. And so this pattern is going to repeat. So each successive half-life is double the previous half-life. And so the next half-life will be twice the previous half-life, or 4 times the first half-life. And so the reaction is going to take a lot longer, whereas over here it's just this regular intervals like this. And so this one's going to be drawn out. Excuse me. And so each successive half-life doubles, so it takes a bit longer. The second order comes from this. If we look at the rate, which is going to be the slope, delta A over delta T, the absolute value of that. And we're looking at the instantaneous slope, or the instantaneous rate. And so let's start here. And so this is the instantaneous rate at time 0, the slope of this. And then if we go to this one, which is T1 half, we have half the concentration. And we look at the difference in the two slopes. It turns out that this slope is 1/4 of our original slope. And so that type of behavior can be modeled mathematically. So we look at this pattern in slopes. That pattern in slopes is going to give us a constant times the concentration of A squared. And so if we cut the concentration of A by half, then 1/2 squared would be 1/4. And so we get this pattern. And so this would be 1/4 of the previous one, or this would be 1 whatever of the original one. And so, excuse me. The opposite holds true. If we go more concentrated, if we double the concentration, the rate should quadruple. Over here, the first order, if we double the concentration, the rate only doubles. It's directly proportional. And so this is the other common nonlinear pattern. And if we want to figure out how much time, well, it's difficult because this is always changing. Always changing. And so the time interval, you know, this delta t, the time interval, and the change in concentration is always changing, you know. For a given amount of time, how much reacts, well, it depends on where you are on the curve. And so this makes it difficult to calculate, and therefore we need the calculus. If we use the calculus, then we come up with this equation, which is called the integrated rate law. And so what we do is we do an integration of this, and we get this, which is going to give us plus kt plus 1 over 8 times 0. And so this has the form y equals mx plus b. And so there's yet one more way of determining if it's second order pretty easily, and that is to make a plot. If we make a plot of the inverse of the concentration versus time, then we're going to see this. It should come out linear. If this is linear, then it's second order. So 3 ways of determining it. 1, analyze the half-life. 2, analyze the instantaneous rates, i.e. the slopes, the tangents, which nobody does. Or 3, plot it like this. So, and then we can figure out how. Now, once we figure out the if it's 0 order, first order, second order, then we have the equations and we can do calculations. The calculations would be, you know, how long it takes, or how much is reacted after 60 minutes or some other time interval. And that's what we're after. We're just after, you know, a simple question like how long does it take for coffee to cool from 85 to 25? We need the mathematical equation. So we need to know, you know, how coffee cools, you know, what the empirical pattern is there, just based on experimental data, and then we can figure it out. Okay, now we have a complication, though, and that is, this is fine for a single reactant. But if we have multiple reactants, then things become more complicated. You know, because it's like a single equilibria. If you have a single equilibrium, it would be just one ice table. But if you have multiple equilibria, then you have more than one ice table. Now, if the multiple equilibria have a common species, then everything's tied together. And so we have a problem when we have multiple reactants. Let's say we have 2 reactants, AA plus BB. This goes to product. And let's keep it simple in this example. In this example, let's say it's first order in A and first order in B. So if it's first order in A and first order in B, okay, then we know what the pattern should look like, because I know how to draw first order decay, which is just be exponential. And so if I plot A versus time like this, then what kind of graph do I expect? Do I expect a linear one? Do I expect an exponential, or do I expect a drawn out kind of exponential type decay? I just expect exponential. So if I cut this in half, it takes t 1/2, cut it in half again, the same amount of time, cut it in half again, the same amount of time. So I expect a curve like this. This is first order. This is first order decay. But this is not what I observed. You know, what would I observe in this case? This is not observed. You know what's observed? Second order. I observe second order. And so if I make a plot of A versus T, it comes out second order. So cut it in half again, takes twice as long. Cut it in half again, takes 4 times as long as the original. And so the observed is second order. Then the question is why? Why do we observe second order and not first order? I mean, it's first order in A. I'm telling you it's first order in A. But why is second order observed?
Is it because of its reaction with B?
It's because of its reaction with B, because, well, I'm making an assumption here. This is what we observe if A initial and B initial are the same. If we start off with A and B the same and it's a 1-to-1, little a equals little b, which is equal to 1. And so what we have is something like this. A plus B goes to product. And let's start off initial the same, 1 molar, 1 molar, and the product whatever. If we lose half of A, right, we lost half of A, then we have 0.5 molar left, right? And so if we lose half of A, let's say we're starting off at 1, we're now down at 0.5. But there's one more complication. And the complication is if A gets it cut in half, what does B do? B gets cut in half. Well, if A and B both get cut in half, then cutting A in half is going to slow the rate down by 1/2. Cutting B in half will slow the rate down by 1/2. And we're going to get a composite effect. 1/2 slowdown from A plus, not plus, but times a 1/2 slowdown from B gives us a 1/4 slowdown overall. And so what the situation is this: the rate depends on both A and B. So if A gets cut in half, that's 1/2 to the first, times B gets cut in half, that's 1/2 to the first. 1/2 times 1/2 gives us 1/4 of our original. And so this is going to be looking like second order. And so what we say is this: it's observed second order because what we observe is the overall order. And so the overall order is given by A plus B. Overall order is A plus B plus, I shouldn't say A plus B. This is wrong. I should say 1 plus 1. 1 plus 1, which is equal to 2. And so it's first order in A. We call that first order in A concentration. And this is first order in B concentration. Means second order overall. Second order overall. Let me give you another example here. This next example is A plus B goes to products. We have 2 reactants here. And let's say I plot, just the concentration of A versus time. If I plot the concentration of A, let's do this. Let's plot the ln of concentration versus A. If I plot the ln of A versus A, in other words, it's going to be linear. That is, when I look at the A versus time plot is going to look exponential. And so, this is first order. This is exponential, constant half-life. This is linear. This is telling me it's first order. But can I say it's first order in A? No, I can't. Because I don't know this. You know what I don't know? I don't know if this is first order in A. If it's first order in A, then it must be what order in B? it's got to be 0 order in B. Because what I observe is the overall order, which is first. And so it could be first order in A and 0 order in B, or it could be 0 order in A and first order in B. Because as B reacts, it's a one-to-one stoichiometry. It's got to hold. So for every mole of B that reacts, I have to have a mole of A. And so it could be or, etc. I mean, we could actually have negative orders too, -1 order. So it could be second order in A and -1 order in B, depending on all this stuff. And so what we have is when we get multiple reactants, we have multiple unknowns. And we got multiple unknowns, and only one equation. We aren't going to be able to figure it out. And so this is the equation. The equation is we don't know what it is. And so what we're going to just say is rate is equal to Ka to the m power, B to the n power. Now, m may or may not equal A. And so m and A don't necessarily have to be the same. A is 1 in this case, little a, the coefficient. And n and B don't have to be the same either, little b. And so this is a one-to-one. It doesn't mean it's first order, because m and n have different origins other than the stoichiometry or the ratio that they react in here. And so we have two unknowns. We have two unknowns in one equation, but we know that m plus n must equal 1. And so how do we figure out what m is and how do we figure out what n is? Well, there's one way of figuring it out here. And this is what we did in lab. And so let's do an example here. An example is crystal violet chloride plus sodium hydroxide. Crystal violet chloride plus sodium hydroxide is going to give us crystal violet hydroxide plus sodium chloride. Okay, crystal violet chloride's colored. Crystal violet hydroxide is colorless, so we can follow this reaction. And so what we do is this. For our experiment, we made, you probably didn't realize this, but we made the sodium hydroxide concentration huge. The reason we did this is so that it would change negligibly over the course of reaction. In other words, if we set this up, crystal violet chloride, we have the initial concentration here plus the sodium hydroxide. And so let's say we lost half of our crystal violet chloride. If we lost half of our crystal violet chloride, that would be minus 0.5 times CVCl initial. And this would be, it's a 1-to-1 stoichiometric ratio, so this would be the same number of moles lost over here, or the same concentration loss. And so here, we make this small, and so we end up with 0.5 CVCl initial, or half of it remaining. This is not necessarily equilibrium, this is just the end. But over here, this is going to be a huge concentration. And so this would be like losing, let's say, a drop of water out of a swimming pool. If I made this sodium hydroxide huge, and the change is like a drop of water, then that means the initial minus the change is just going to be the same as the initial. In other words, the simplifying assumption. And so this is going to just be equal to the NaOH initial because it's barely going to change. And therefore, over the course of this reaction, if the sodium hydroxide concentration does not change over the course of this reaction or barely changes, that means it's not going to impact the rate. The only thing that's going to impact the rate will be the change in the crystal violet chloride concentration. And therefore, if we plot crystal violet chloride concentration versus time, we'll see what the crystal violet concentration, the order with respect to crystal violet concentration is. And that is, let's say we do crystal violet chloride versus time. And we already saw it's nonlinear. The only thing is, well, is it nonlinear first order or is it nonlinear second order? You know, those are the two options. There could be more. Definitely could be more for two reactants, but we aren't going to look at those. And so the only thing is it first order or second order? Well, we can see. The way we're going to see that is by making a plot. We're not going to analyze half-lives. We're just going to plot this. And so we're going to make two plots. We're going to plot ln of the crystal violet chloride concentration versus time. And then we'll plot 1 over the crystal violet chloride concentration versus time. And this one is going to go down. This one's going to go up. And then we fit these with a trend line, a linear trend line. In Excel, we can do that. And they're both going to kind of look linear. And so in Excel, we're going to do this. We're going to add trend line by right-clicking on a data point. The default option is linear, and so we'll just leave it as linear. And then on the bottom of the formatting window on the right, we select the bottom two check boxes, display equation and display R squared. The R squared is something we want to pay attention to, because the R squared, this is called the correlation factor. Correlation factor tells us how the data fits the trend line. So for example, if each data point lines up exactly on the trend line, that is, if it's a perfect fit, then the R squared is equal to 1. That would be exactly 1. That is, every single data point is on the line. We aren't going to see a 1 unless we had 2 data points. We're going to see something less than 1. And so what we're looking for is something like this. You know, the closer to 1, the better. So we're looking for like 2, 3, 4 9s. If we get 4 9s, oh, that's pretty good. If we get 3 9s, that's pretty good. If we get 2 9s, well, that's pretty decent. If we get 1 9, that's not so good. 1 9, do you think that's pretty good? Let's say if I got a 9.94, a 0.94 is not a very good R squared. It's not a great correlation. A 0.94, you know, it would be something like this. This would be a 0.94 here. And so we're looking for something better. So this is not great here. This is great. If we're in the 0.8s, then forget it. That's really bad. 0.8. And so what we'll do is we'll compare the R squareds. What was the R squared here versus the R squared here? We could even do an R squared here. If we did an R squared here, this is clearly nonlinear. This R squared is going to be maybe 0.89 or something, maybe 0.9. So we'll see. All right, for purposes of this, let's say this one gave us the highest R squared. This lab, the ln. If this one gave us the R squared closest to 1, and then we suspect that this should be first order in crystal violet chloride. And way this should behave is predictable. And so so if the natural log of the concentration versus T is linear, then first order in CbCl is about chloride. And so that means the rate is going to equal K times K, which is the rate constant again. And the rate constant, we have to figure out what that is. But it's going to be CbCl to the first power here. So this means M equals 1. M equals 1. And this would be the sodium hydroxide to the nth power. So what this means is if I double the concentration of crystal violet chloride, then the rate of the reaction should double. If I cut the concentration of crystal violet chloride in half, the rate should be cut in half. This is assuming that sodium hydroxide is so big it doesn't impact it. And this has to be big. If this is big such that it's relatively constant, then this is what we'll do. We'll make this what we call pseudo-M order. Pseudo-M order. Pseudo-M order just means this. This is so big that we're going to wrap it into this constant. So we'll combine the two constants, K and the sodium hydroxide. And so the rate is going to equal K prime times the CbCl. Since the sodium hydroxide doesn't change, we'll just put it into the constant and we'll make the constant bigger at first. And this is M here that we determined M as 1. And so if we did this reaction with a huge sodium hydroxide, huge excess, this is a big waste of sodium hydroxide, because we're using a huge excess, and most of it's not going to react. So if we do this huge excess of sodium hydroxide, then we can make predictions. How long will this take? Well, it's just first order. We use all the equations for first order. But what if we didn't have a huge concentration? Then we need to know what N is. And so how do we determine N? Because what if I didn't want to use a huge excess of sodium? What if I just wanted, let's say, 1 molar crystal violet and 1 molar sodium hydroxide, or 0.1 molar, 0.1 molar? If I had the same concentration initial, or if they are close initial, then I need to know, because if I have, let's say, 0.1 molar crystal violet and 0.1 molar sodium hydroxide, then by the time the crystal violet's cut in half, the sodium hydroxide will also be cut in half. And if the sodium hydroxide is cut in half, that's going to change, or it could have an impact. It depends. If N is 0, then it won't have an impact. But if N is 1, well, if this is cut in half and this is cut in half, then the overall rate would be 1/4. Or if this is 2, let's say it's second order in sodium hydroxide. If this gets cut in half and this gets cut in half, then it'd be 1/2 times 1/2 squared, which would be 1/8. And the rate would be 1/8. And so it'd be a different kind of decay. One decay that I haven't shown you. And so we got to figure out what N is. For N, we will use a modified version of the method of initial rates. The method of initial rates. Method of initial rates. Well, let's. What is the method of initial rates? So let me give you an example of the method of initial rates, and then let's see how we're going to modify it. Now, first off, what is the initial rate? The initial rate is the rate at time 0. the rate at time 0 we can get from the graph. And so if we have a graph like this, what we'll do is we'll just draw a tangent line at time 0. And so the initial rate is equal to the slope of the tangent at time 0. In other words, it'd be the rate at time 0. The instantaneous rate at time 0. Instantaneous rate at t0. Well, drawing a tangent line at time 0 is not easy. Since it's not easy, then alternatively, we could do this. The initial rate is about equal to, this is better, of course, but the initial rate is about equal to the average rate when less than 95% reaction has occurred. And so if we look at it, let's say we started off at 1.0 and we go down to 0.95. It depends if we have a data point. Let's say we have a data point here initially, and we have a data point that falls within this range of 1.0 to 0.95. In other words, the first 5% of reaction. And although this is a curve, right? This is some kind of curve. What we're going to do is we're just going to go ahead and take the average rate here. And so we'll just take the first two data points and calculate the slope. And so we aren't going to draw the tangent line at time 0. We're just going to take the first two data points and get the slope of that. That gives us the average rate over this time interval from t0 to t, the first data point. And so this is the average rate. Since it's right at the beginning of the reaction, it's going to be close. Not exactly, but close. And so this is why we say approximately equal. Well, this is a lot easier than drawing tangent line at time 0. Just take the first two data points. As long as it's less than 5%, that's going to be your initial rate. The problem is did we measure the data at time 0? No, at time 0, half your CV was still inside the burette. At time 0, we have no data at time 0. We can't even draw a tangent line at time 0. By the time you dropped the remaining part of the crystal violet into your beaker, do you think more than 95% reactions occurred? Yes. We missed that time window. And so we cannot do the method of initial rates. But if we did have the data for the initial rate, then it'd be pretty easy, because this is what we do in the method of initial rates. We know the initial concentrations because that's what you mix together. And so what we do is solution dilution, figure out the initial concentrations. And if we know the initial rate, then we know what the rate was for those specific concentrations. So we make up a table like this. The rate, the concentration of A, the concentration of B. And so this would be for run 1. So run 1 has a rate 1, so we'll call it rate 1. And that's going to have initial concentration 1, initial concentration 1 for both A and B. Then we do this. We double A. If we double A, then we'll make A twice as concentrated as run 1. And so A for run 2 is double the concentration, but we leave B the same. And so B is not going to have any impact because it's the same concentration. It won't change the rate. And then we look at what happens to the rate, 2. So this is what's going to happen. If we double the concentration, nothing happens to the rate. The rate stays the same. That's 0 order. There's no dependence. That's option 1. Option 2, we double the concentration and the rate doubles. If we double the concentration and the rate doubles, that's first order. And then option 3, we double the concentration, the rate quadruples, that's second order. And so with the method of initial rates, we can easily figure out, we just look at what happens to the rate. Did the rate stay the same? Did the rate double? Or did the rate quadruple? And that's it. And then we go on to figure out B, what B is. And so we'll have to do a third experiment. For B, we leave A the same. And so we'll leave it as same as run 1. And so that's going to have no impact. And then we double B. So we make B twice as concentrated. And then we do the same thing. If we double B, what happens to the rate? Did it stay the same, double, or quadruple? And that'll tell us, is it 0 order, first order, or second order in B? And therefore, we can figure out what M and N are just by doing the method of initial rates. Actually, this is a pretty easy way to determine it. A to the M, B to the N. And so we can figure out M and N by doing 3 trials. Did we do 3 trials? No, we didn't. We did 2 trials, and we're going to be able to figure out what M and N are based on 2 trials rather than 3 trials. 3 trials would be required in the method of initial rates. But we're doing only 2 runs, and we should be able to figure out. We should be able to figure out because we're doing 2 runs, and both of them are pseudo M order, and so that takes care of M. We can figure out what M is based on the plots. Now, what did we do? We did sodium hydroxide, and we doubled the sodium hydroxide. When we doubled the sodium hydroxide, did the reaction take half as long or a quarter as long? In other words, did that reaction happen twice as fast or 4 times, or did it happen the same speed? When you doubled the sodium hydroxide, did the reaction happen faster or the same? The same? Okay. Well, that's something we could figure out based on the time. The time it takes to go from, let's say, 0.6 absorbance down to 0.05 absorbance or something like that. But what we're going to do is we're going to do the modified. Because we did not measure initial rate. And so the modified version is this. Which run was, actually one run was faster than the other. Do you know which one was faster? The drop? Actually, can somebody look in their notes and tell me, run 1, was it 5 mils of sodium hydroxide or 10 mils of sodium hydroxide? 10 mils? Okay, run 1 actually turns out to be faster. And so we have run 1, and we're going to take a ratio, run 1 to run 2. By looking at the rates. So we're going to have rate 1 over rate 2. Now rate 1 is just equal to K, the rate constant, times the concentration of A to the nth power, B to the nth power. And rate 2 is K, A to the nth power, B to the nth power. Now, concentration of A in run 1 and concentration of A in run 2 are the same. We didn't change the concentration. The concentration of B in run 1 is not the same as the concentration of B in run 2. And so K is the same actually because it's the same reaction. A is the same. And so what we end up with is B1 to the N over B2 to the N. Well, it turns out that B1 is 2 times B2. It was double B2. So 2 times B2 to the N divided by B2 to the N. Well, B2's cancel here, the N. And this gives us 2 to the N. The problem is did we measure the initial rate here? No. And so this is unknown. We don't know what that is. But whatever it is, it's equal to 2 to the N. And so we have to do a little bit more. Well, a little bit more is we also did pseudo M order. And so for our reaction, maybe I should write this in terms of crystal violet chloride. For our reaction, this is so far what we're going to have. We're going to have 2 to the N and this came from the sodium hydroxide, which is B. B equals sodium hydroxide, A equals crystal violet chloride. And so this is going to equal K. Now, we made the sodium hydroxide so concentrated, we combined it with the constant. And so this will be K prime times the crystal violet chloride concentrate. Yeah. 1 to the M. And this will be K2 prime. This will be K1 prime times the crystal violet chloride concentration initial to the M. Well, we did the same crystal violet chloride concentration on both of these. This is where K prime is the K prime 1 is the constant K times the sodium hydroxide concentration, which is so large from run 1. Excuse me. And then K prime 2 is K times the sodium hydroxide concentration from run 2. And the sodium hydroxide concentrations are different. And so this would be the sodium hydroxide to the N, sodium hydroxide to the N. And so what we're going to get is this. We're going to get 2 to the nth is equal to K prime 1 over K prime 2. The K prime 1 and K prime 2, we're going to get these from the plot. So if it's 0 order and first order, then K prime is equal to the negative of the slope, or the absolute value. If it's second order, then K prime is equal to the slope, not the negative of the slope. It's the slope. So once we get that information, then we get N. In other words, did they react at the same rate? No, they reacted at different rates, so the rate constant is different. One of these is bigger. K1 is bigger because we had twice as much hydroxide there. Okay, from this, we'll be able to calculate the Ks. You can calculate the K that we got from run 1 and the K from run 2. And then we'll get the average K. Because the K should be the same. All right, so from all this, what we're going to do, and this is the goal of this experiment, the goal of this experiment is to get the rate law. And the rate law is going to be the crystal violet chloride and the sodium hydroxide concentration dependence here. And so what we want to do is we want to determine K. We'll get K from the K primes. We'll want to determine M, and we'll want to determine N. M we get from the graphs, N we get from doing this, ratios, initial rates. And then we're done. This is the goal of the experiment. Okay, once we have this, then all we can do is say this. If we double the crystal violet and we double the sodium hydroxide, what happens to the rate? If we cut this in half and we quadruple that, what happens to the rate? That's all we can do. If we want to calculate time and amounts, then we need calculus. But in this case, we need multivariable calculus, which is beyond the scope of this class. And so we need to generate the other equations for this. But we aren't. And so we're just going to stop here, and we're not going to answer how long it takes or how much. We only do that for single variables. And we can make a multivariable into a single variable by making one of the variables so huge it doesn't change much. And that's it. All right, so that's what we're doing in lab today. And so we're going to move over into the computer lab, and we're going to analyze our kinetics data. We'll do it together. So just head on over to Chem 108, the chemistry computer lab, and we'll start looking at our data and working it out.